Welcome to this video on digital electronics. In this video, we will be discussing about Boolean algebra. We look into Boolean postulates and Boolean theorems, sum of products and product of sums, and the canonical forms. Boolean algebra is maths for digital electronics. Boolean postulates are the basic assumptions from which Boolean theorems are derived. We shall first look into Boolean postulates, but before that, let's get familiar with some of the terms used. Variable. It is a symbol that represents a logical quantity in Boolean algebra and it can take the value of 0 or 1. Example of y is equal to a plus bc, a, b, c are Boolean variables. And next, constant. In Boolean algebra, the constant, there are two values, 0 and 1. And complement, if a is equal to 0, the complement of a indicated by a bar or a dash a prime is equal to 1. And if a is 1, the complement is 0. That is, complement is taking the naught or inverting the value. And a literal, a single variable within a term that may or may not be complemented is called a literal. And Boolean functions, they are described using Boolean expressions. Example is f of a comma b comma c is a plus b c, where a, b, c are the variables. The three basic Boolean operators are AND, OR and NOT. So let us look into these operations. The truth table is indicated. First, considering AND operation. So we shall consider for two variables. If x and y are the two variables, then the AND operation results in a value of 1 only if both x and y are 1. If either of the values are 0, the output is 0. So looking into the table, for x value of 0 and y 0, x and y indicated by the symbol x dot y is 0. For 0 and 1, x dot y is 0. For 1 and 0, it is 0. And for 1 and 1, it is 1. Next, considering the OR operation, x or y. If either x or y value is 1, then the output is 1. So looking at the table, x of 0 and y of 0, the output x or y is 0. But for x of 0 and y of 1, the output OR operation is 1. And for 1 or 0, the output is 1. And 1 or 1, it is 1. Considering the NOT operation, if x is 0, x naught is 1. And if x is 1, x naught is 0. X naught can be indicated by x bar or x prime. Looking into the postulates. First is the closure property. So with respect to the AND or OR operation. So when two binary numbers are operated by either an OR or an AND operation, the result is again a unique binary element. Therefore, it is closed with respect to AND and OR operations. To understand this better, let us consider algebra, where the sum operation, for a set of natural numbers, the sum operator is closed. For example, if you take 5 and 3, two natural numbers, when you add them 5 plus 3, we get 8, which is again a natural number. So for a set of natural numbers, the operator sum or plus is closed. Whereas consider minus. For a set of natural numbers, the minus operation is not closed. Let us look at y. 3 minus 5. 3 and 5 are natural numbers, but 3 minus 5 yields minus 2, which is not a natural number. So it is not closed with respect to minus operation. So similarly here in Boolean algebra, for the plus and dot operations, the binary numbers, they are closed. Next, identity element. So for the OR operation plus, the identity element is 0. So a or 0 is equal to 0 or a, and it is a. You can substitute the value of 1 and 0 for a and verify the result. Similarly, for the dot operation or AND operation, 1 is the identity element. A dot 1 is equal to 1 dot a is equal to a, or a and 1 is equal to 1 and a is equal to a. Next, the commutative law. A or b is equal to b or a. And similarly, a and b is equal to b and a. Associative law. A or b or c, the brackets is parenthesis are within b for b and c. If the parenthesis is shifted to a and b, it yields the same result. And similarly for A dot B dot C, if the parenthesis is shifted, they are equal. So that is associative law. Distributive law, A dot B or C, B or C is within parenthesis, is equal to A dot B or A dot C. The parenthesis, that is A dot is distributed among B or C. Similarly, A or B and C is A or B and A or C. So that is distributive law. And inverse, for every binary element there exists a complement element. So for A bar is the complement, and if A is equal to 0, A bar is 1, or if A is equal to 1, A bar will be equal to 0, and it can be represented as A bar or A prime. And also A plus A bar is 1 and A dot A bar is 0. So all these proofs can be given by perfect induction method, that is, draw the truth table, write down the individual variables value, consider all the combinations of values for the variables and check the result, perform the operation and check the result. We can thereby prove the laws, the postulates. So the postulates can be proved by perfect induction method. Next, we shall consider an important principle, the principle of duality, which states that starting from a Boolean function, we can derive another Boolean relationship by changing each OR sign to an AND sign or an AND to OR and complementing the ones to zeros and zeros to 1. Thereby another relationship, a dual relationship, can be obtained. That is, to summarize, to get the dual of a Boolean relation, replace the plus operator by a dot operator or an AND operator, the dot by a plus, and replace 0 by 1 and 1 by zeros, and thereby we get the Boolean relation. Now looking into the basic Boolean theorems. The first, idempotency theorem, which states that A plus A is A, that is A or A is A, and A dot, the dual of it, replace a plus by a dot and we get A and A is A. This proof can be seen by perfect induction method. The next is the full set or null set theorem, that is A or 1 yields 1 and A and 0 yields 0, which is a dual of it. So you can see if either A takes a value 0 or 1, 0 or 1 will give a 1, 1 or a 1 will also yield in a 1. Then the involution theorem, which states A complement of complement is A, that is A dash dash, taking double complement of a variable results in the same variable. As you can see, if A is 0, A dash gives 1 and A double dash gives 0 again. So A double dash is equal to A. An absorption theorem, which states A plus AB is A and A plus A bar B is A plus B, the proof of which we shall see later, and the dual of it is given. Associative law, A plus B plus C, where a parenthesis for B plus C, if it is shifted to A plus B, it gives the same result, which can be proved by perfect induction method. Then the consensus theorem, which states that AB plus A dash B plus BC is equal to AB plus A dash C, the proof of which we shall see later. And next, a very important theorem, the De Morgan's theorem, which states the complement of product is equal to sum of complements. AB the whole dash is equal to A dash plus B dash. And similarly, the dual of it is complement of the sum is equal to product of the complements. So A plus B the whole dash is equal to A dash dot B dash. The proofs for the two laws, absorption law and consensus theorem. Absorption law, we saw it states A plus AB is equal to A. So we will prove that. By distributive law, we can see it can be given as A into 1 plus B, and we need results in A. So the law is proved. Similarly, A plus A dash B, the result is A plus B. We shall see how to get it. Replace A by A plus AB and write A dash B as it is. Now regroup it. So A plus, by distributive law, take out B into A plus A dash. a plus a dash is 1, this results in a plus b. Similarly, for the consensus theorem, ab plus a dash c plus bc, include another term a plus a dash which is equal to 1, which can be included with bc. Now rearrange the terms, expanded by distribution law first. So ab plus a dash c plus abc plus a dash bc. Then rearrange the terms. From the first and the third term, take ab common is into 1 plus c. From the second and the fourth term, a dash c is common, so it's 1 plus b. And so a that is equal to ab plus a dash c. Pause the video, solve the problems. Pause the video again, check your answers and then proceed. Next is Boolean functions. So first, literal, what we've already seen, it's a single variable within a term which can be primed or not primed, that is it can be complemented or not. Then Minterm, which is nothing but a standard product term. So it contains all the literals either in the complemented or uncomplemented form, and it is an AND term and represented by small m to the suffix I. So examples are, if there are 3 variables, then a, b dash c. It is a Minterm, that is it contains all the 3 variables a, b and c either in the primed or unprimed form. Similarly, a dash b c. Next is max term, which is a standard sum term. Here again this term also contains all the variables or all the literals in the complemented or uncomplemented form, and it is formed by an OR term and represented by capital M to the suffix I. Examples are a or b dash or c. So if there are 3 variables a, b, c, all 3 are available and they are all odd, and they are either in the primed or either in the complemented or uncomplemented form. Next, Boolean expression. It is constructed by connecting Boolean constants and variables using Boolean operators. Example, function of a, b, c is a dash plus b into c, or that can also be represented as f is equal to a dash plus b into c. Next is SOP, sum of products, or POS, product of sum. So the terms that form the function may contain 1, 2 or any number of literals, not necessarily all the literals. So the terms which can contain either 1, 2 or 3 or any number of literals forms the sum of product or product of sum. So sum of products, that is product AB and B dash C, the sum of it gives the sum of products. Note AB, this term, product term, has only 2 of the 3 variables. It has only AB, and the next term has only BC, doesn't have A. So sum of product term, it is a function which could contain 1, 2 or any number of literals, and it is a sum of the products. Similarly, product of sum, it is the product of sums. Next, the canonical form or the standard sum of product or product of sum. Here it is expressed as sum of minterms. A standard SOP or canonical SOP is the sum of minterms, that is sum of the product terms where all the literals are available. And standard POS or canonical POS is the product term of max terms. So the example over here, standard SOP is ABC dash plus AB dash C. Notice the minterms over here, that is all the variables are available. And standard POS or canonical form is a plus b dash plus c into a b dash plus b dash plus c. So 2 sum terms which are ANDed. The 2 sum terms have all the variables in the complemented or uncomplemented form, that is they are the max terms. We shall see how to convert a sum of product to the canonical sum of product. So before going by the rules, we will consider one of the examples. Here y of a comma b is given as a plus b. Notice there are 2 variables a and b, but the first term has only 1 variable a, b is missing, and second term has only b, a is missing. So to get a minterm, that is the standard product term, and a with 1 and b with 1. So now a dot 1 can be replaced as a dot b plus b dash, because b plus b dash yields 1, which does not change the value of the function. Similarly, b dot 1 can be replaced by b dot a plus a dash, By distributive law, expand the expression and remove the repeated product terms, and we get the standard sum of product. Here you observe every product term has both the variables of the function. Note here all the product terms have all the variables of the function. Moving on to the steps for conversion of sum of product to canonical or standard sum of product. First, find the missing literal in each product term. Then add the product term with missing literal and its complement. Expand the terms and reorder the literals. Omit the repeated product terms and we get the standard or canonical sum of product term. Considering the second example that is given, y of a, b, c is a plus bc. The first product term a, the variables b and c are missing. So, AND it with the missing literal and its complement. So, a dot b plus b dash into c plus c dash. And in the second term, a is missing. So, it's a plus a dash into bc. Now, expand using distributive law, rearrange the literals and omit the repeated product terms and we get the standard sum of product term. Again observe every product term has all the three variables either in their complemented or uncomplemented form. So now pause the video, solve the problem, check your answers and proceed. Similarly, proceeding with conversion of product of sum term to standard or canonical product of sum term. First step, find the missing literal in each sum term, then OR each sum term with missing literal and its complement. Expand using distributive law and omit the repeated terms. So, the example of a dot a plus b plus c, the first term b and c are missing. So, this can be written as a plus b dot b dash and c dot c dash. And then we know from the distributive law a plus b c is a plus b into a plus c. So, use that over here. First c dot c dash is considered and two sum terms are obtained. Next here consider b dot b dash and get a plus b plus c and a plus b dash plus c. And for the next term again consider b dot b dash over here and expand it and rearrange and omit the repeated terms, we get the sum term. Here again observe in the sum term all the sum terms have all the variables present in them. Pause the video, solve the problems, pause the video again, check your answers and proceed. So, representing the min terms and max terms for three variables in a tabular form truth table. Notice the variable, the first column gives the variable, three variables a, b, c. All the combinations from 0, 0, 0 to 1, 1, 1 are represented and the terms, min terms are represented by a, they using the variables. So, the first min term is a dash, b dash, c dash. A 0 is represented by the complemented form and a 1 by the variable as it is in the unprimed form. So, 0, 0, 1 is represented by a dash, b dash, c and then 0, 1, 0 by a dash, b, c dash, so on up to 1, 1, 1 that is a, b, c. They can be represented as min terms as m0, m1, m2, m3 etc. up to m7. The suffix is equal to the decimal equivalent of the binary values. Next, considering the max term for 0, 0, 0 is given as a plus b plus c. Here zeros are represented in the uncomplemented variable and 1 by the complemented variable, and observe this 0 term a plus b plus c is the complement of the min term a bar, b bar, c bar. Use De Morgan's theorem, complement a bar, b bar, c bar, we get a plus b plus c, that is the max term representation. So, similarly all the max terms are represented with 1, 1, 1 being represented by a dash plus b dash plus c dash. And they are designated using capital M, the suffix representing the decimal equivalent of the binary number. Observe the max term m of j, capital M of j is equivalent to the complement of the min term, that is mj dash. Moving on, how to form the canonical form from the truth table. For the function y is equal to a plus b dash c. So for that the output is given, the inputs a, b, c, all the combinations are there, and the output y for the function a plus b dash c. So now consider all the minterms for which the output is 1. So 1 is a dash b dash c, then next is a b dash c dash, then a b dash c, a b c dash, and a b c. So all the 5 combinations it's taken up and written, and that is the standard sum of product term, and which can be designated by M1, M4, M5, M6 and M7, and it can also be written as sigma M of 1, 4, 5, 6, 7. So this is how we get the canonical form from the truth table. Now this was the sum of product term. To get the product of some terms, consider all the terms that have a 0 and represent the max terms. So it is a plus b plus c, a plus b dash c, and a b dash c dash. So sum of product of all these terms is equivalent to y. This can also be shown as, we know the output here is 0, that means y dash, the complement of the function, is equal to sum of these minterms. Taking a complement again, we get this term which is equivalent to getting the product of the max terms, represented as m0, m2, m3, and equivalent to pi capital M of 0, 2, 3. So from the truth table, the canonical sum of product or product of sum can be obtained. To get the sum of product term, consider all the values of output for which output value is 1 and get the minterms and sum them, that is a result. To get the standard product of sum terms, consider the values for which the output is 0, take the max terms for them, and then multiply or find the product of the max terms, that gives the POS. Pause your video, solve the problems, pause the video again, check the answers, proceed. So in this video on Boolean algebra, we have seen the basic Boolean postulates and the Boolean theorems that have been derived therefore. We have also seen some of the important terms used in Boolean algebra, then what sum of product and product sum of sum is, and how to convert SOP or POS into standard or canonical SOP and POS. And we have also seen how to get the canonical forms from a truth table. These are the references used. Thank you.